Any questions about anything from last time? Yeah.
Will there be any lecture material on Friday?
I'm going to lecture on Friday, yeah.
Will there be any material or will it be review?
No, I still have some loose ends to finish up, but then review is next week. And I'll put out some practice problems to talk about next week. Give you a chance to look at them before I show you the solutions. Well, let's say I should point out that the last homework 9, is due. I extended it to Friday at 11:30 p.m. Put some hints on Piazza for you to see about one of the problems. There was a loose end last time. I mentioned that I was solving a hot wire problem. Was there another question? Oh. There was a hot wire problem I was working on. It was a wire stretched from 0 to pi along the real axis, and I was keeping the right end point at pi 0 degrees. But the left end point was only known to be insulated, so no heat flow across that left edge. Of course, we would expect the solution, the heat, to drain out and go out through that right end, and eventually the solution would be 0. And that's exactly what does happen. There was an e to the minus something squared t in every term, and that makes everything go to 0 very rapidly. So the heat gets sucked out of the right end point. And that formula for the solution converges fast enough that it's useful in using, say, maple computations. The terms go to 0 very rapidly because of the negative exponentials. Anyway, that thing that we dealt with is a general Fourier series, a generalized Fourier series. Because notice that if I was trying to satisfy the initial condition, then the problem boiled down to expanding f as a sum of cosine n plus a half x terms. Those are not the usual. That's not the usual Fourier series. The usual cosine series would be cosine nx, not n plus a half. And so the question is, it felt like the same old theory, but we haven't shown that kind of thing converges. Well, there's a big theory around Sturm-Liouville problems where they all come up with orthogonal functions that you can use as building blocks and sort of you reinvent Fourier series every new problem you do that way. And it works in the general case, and it's just a little more work to make the theory all down on papers. You'll read about it in more advanced books. But I wanted to show you that this particular case, we can determine that this converges, just like Fourier series. In fact, just like a Fourier cosine series. So let me show you what the trick is. Last time I told you, if you get desperate enough, you'll try anything. Well, I hadn't prepared this last few seconds of the exam, and I forgot exactly how you do this problem. So in my desperation, I suggested that maybe we would try extending the function f as an even extension on the right-hand side there. Well, that turns out not to work. I was wrong. I was desperate, but I was wrong. Now I sat around and thought about it more, and I remembered how to do it. So I've got this function f. It's only defined on 0 to pi. That's the initial temperature distribution of the wire. And we had the boundary conditions. The insulated end would have 0 temperature gradient. So we would probably have a function f such that f prime of 0 is 0. So there's no heat flow across the boundary. And f of pi was held at 0. So that's the type of function we're looking at. Okay, so I'm going to somehow relate this new kind of Fourier series to a regular Fourier series. And I'll explain how I'm going to do it. So see that green function, f of x? That's my f of x from 0 to pi. I'm going to first extend it from 0 to pi to 0 to 2 pi. And I'm going to extend it as an odd extension about the point pi. So I think of pi as my new origin. And so if you think about the odd extension, if I go a little distance here to the left of pi, if I have a negative value, then to do the odd extension, I'd go to the right of pi and make that same distance. Those would be equal. But of course, they're opposite sign. That's the odd extension. And so that blue thing is the odd extension about pi. Okay. Then the next thing I do, I've got a function now from 0 to 2 pi. I'm going to extend that as an even function to the other side. So the next step, I extend it as an even function from 0 to 2 pi to the whole interval from minus 2 pi to plus 2 pi. So that's just a reflection to the left. Okay, so now I get a function from minus 2 pi to 2 pi. And if I wanted to extend it to r, then I would extend it as a 4 pi periodic function. And I get a new function that way, which I'll call f star. So this thing right here is a graph of f star when I do all the extending. Well, if you think about, now I'm going to expand f star in a Fourier series. Remember, if the coefficients in Fourier series, in the general Fourier series, where you use a length L instead of 2 pi, you use length L instead of pi. In this case, I'm using L equals 2 pi. And so notice that you're going to get cosine n over 2 x when you do that. It'd be n pi over 2 pi, n pi over L. That's what that is, the n pi over L. So it'd be n pi over 2 pi is n over 2x. That includes my cosine terms. Remember, mine were the odd multiples of 1/2. 1, 3, 5 over 2, etc. So that includes terms just like my cosine series. But it also includes other terms. The interesting thing is that extension I did is going to make all the terms I don't care about 0. So that's going to take some, let's just think about it a little bit. Good news is because I took an even extension to the other side, the left side, all the bn's are 0 because f star is an even function. So all the sine terms go away. That's looking good. Also, think about a naught. A naught is the average of the function. And let's see, the odd extension over there would make those areas cancel. And the same thing would happen on the left. So there's 4 areas, and they're plus, minus, plus, minus. So the 4 areas cancel, and the average is equal to 0. So that's nice. So that's because the average is equal to 0. The average of f star on the whole interval minus 2 pi to plus 2 pi is 0. And now I claim that the an terms, the cosine terms, are 0 for even n. And that's not hard to see because let's do n equal 2. So a2, the formula for the coefficients from minus 2 pi to plus 2 pi is 1 over L, L is 2 pi, times the integral from minus 2 to 2 pi of something. But those functions are even, remember, so that would be 2 times the integral from 0 to 2 pi. Okay, and that's the right-hand side of the green one. and the blue one, which I took an odd extension. So if you think of that integral, and you think of the origin now as being at pi, then that function f star is odd about pi. And the cosine x term, let's see that, for n equals 2, that would be 2 pi over 2 pi. That's 1 times x. So the function in that integral would be just cosine x. And cosine x is even about x equal pi. Let me draw that on the graph so you can see that. Let's see, what does cosine x look like? It looks like, I'm going to cross this out in a second. Cosine is plus 1, and then it goes down and is minus 1, and then it goes back up, and it's 2 pi periodic. So sure enough, that's not a very good graph, but cosine looks pi over 2 here, then it's minus 1, and then it goes up like that. That is symmetric about pi. Okay, symmetric about pi. So if you think about my integral there, I've got an odd function about pi and an even function about pi. That thing integrates to 0. And same for all the rest of them. Same for n equals 4, 6, 8, etc. All right. So this is getting exciting. Now let me think about the odd terms. Let's think about n odd. Let's do the A1 term. A1, for example, that would be 1 over 2 pi, integral from minus 2 pi to 2 pi. And the function's even. So that would be twice that from the integral from 0 to 2 pi. And here's an interesting thing. That is equal to, let's see, what is it? I've got my f star. And then I would have cosine, at 1, this would be 1/2 x dx. And that is, let's see, remember this is odd about x equals pi. But cosine 1/2 x is actually even about x equals pi. No, it's odd. Is it? Let's see, cosine of pi over 2 is 0. Yes, it's odd. Okay, so that's going to be even, so that's odd about x equals pi. And so when you multiply two odd things, you get something that's even. Okay, and therefore this is going to be 2 times the integral of half from 0 to pi. And from 0 to pi, f star is the same as f. And here I get cosine x over 1/2 x dx. And that's the formula I was hoping for. So the coefficients in that Fourier series are exactly the ones I needed to analyze my sum of cosine half terms. Okay? Questions about that? Yeah.
For n
Right, so it's going to be 1/2, 3/2, 5/2, etc. And all those functions are going to be odd about x equal pi. So I get odd times odd is even. Yeah. So let's see, y is cosine half, I should graph cosine half x. This is 2, this is 0 to pi. Cosine of half x would go, that'd be pi over 2. So cosine of pi over 2 is 0. And then it would go down and be like this. So this is a graph of cosine x over 2. And you see that, yes, sure enough, it's odd about x equals pi. And 3/2 that would be doing something very similar. So I don't want to get carried away with this, but same for cosine 3/2 x, cosine 5/2 x, and all the rest of the odd terms. So that means the Fourier series so the aha moment here, the series summation n equals 0 to infinity an cosine n plus 1/2 x is the full Fourier series for f star on the interval minus 2 pi to plus 2 pi. And notice that something interesting, that graph of it, let's say f is C1 smooth up to the edges. Well, the fact that that slope is 0 at the origin means when I glue them together at the bottom there, at the other ends, minus 2 pi and plus 2 pi, when I glue them together and make it 2 pi periodic, that 0 slope hooks up, and my extension would be C1 smooth. And the same thing happens at, say, pi. The odd extension would have the same slope, and they'd hook up there, and it would be C1 smooth at that spot where I extended it. So if f is C1 smooth, my extension is going to hook up and be C1 smooth, and I'll get fantastic convergence even at the endpoints. So nothing weird is going to happen at the endpoints. And what's interesting now is I have a Parseval's identity. So remark, this yields that we have a Parseval's identity, which is exciting. Let's see, so the Parseval's identity is that 2a0 squared plus the summation as n goes from 1 to infinity of an squared plus bn squared. Let's see, we have an L here now, where L is equal to 2 pi. And so the Parseval's identity said this would be 1 over L integral from minus 2 pi to plus 2 pi of f star squared dx. And remember, these are all 0. These are all 0. And the capital ANs are, every other one of them is 0. And this boils down to the summation as n goes from 0 to infinity of the an squared. Those are real numbers, so I won't put the absolute values. Okay, that's kind of cool. And over here, f star had some various kind of extensions. This will be 1 over pi times the integral from 0 to 2 pi. It's even. That was an even extension. And then I know the fact that that odd extension to the other half of 0 pi to pi, from pi to 2 pi, that would be equal to 2 over pi of the integral from 0 to pi. Because that odd extension would have the same area under the graph of the f star. And so that would be the same as this, times 2. And so I get a Parsifal's identity like that. And that Parsifal's identity is equivalent to completeness of that orthogonal system. Questions about that? If you're in an engineering class where you really wanted to solve heat problems like that, all of them work out in this condition. Work out like this, and you'd learn various cases and how to extend the function to make it all work. So let's see, we get Parsifal's only when f is continuous. This works when f is merely continuous. When f is C1 smooth, with f prime of 0 and f pi equals 0. Let's see, f prime of 0 is 0. And f of pi is equal to 0. When f is C1 smooth, f star is C1 smooth on all of the real line. C1 smooth. And you show in your homework that that means the Fourier series is absolutely convergent. And that means the solution converges uniformly. The series converges uniformly. And the Fourier series is the funny cosine series, the generalized one. Uniformly to the desired limit f star. So I'd restrict to 0 to pi and know that it converges uniformly to f on 0 pi. Converges uniformly to f on r. And so uniformly to f without a star. On 0 pi. If I was going to dwell on heat problems and do more Sturm-Liouville examples, there's another possible boundary condition. That's if you're going to study this as a engineer, that you'd be thinking about for a week probably. Another possible boundary condition, which is interesting, that leads to more generalized Fourier series that are pretty interesting. So we've had the homogeneous boundary condition. let's see, we had du dx at 0t equals 0. That's the insulated end. The u of x comma t, u of 0 comma t, 0 for all t. That's the homogeneous boundary condition. I think of that as the refrigerated end. I slap on a refrigerator, keeping it at 0 degrees. Homogeneous boundary conditions is nice because it means you can add them together and get more solutions. Well, here's the radiate. This is called the radiative. You've heard of infrared heat. So the radiative boundary condition, when something's red hot, that red color, that's it's bleeding energy out by radiating heat. And so if it's bleeding out heat, then it would definitely be cooling. And so the radiative boundary condition is that, let's see, what is it? The rate of heat loss. Okay, that would be equal to the heat flow. The rate of heat loss, that would be the rate of heat flow. And we know by Kelvin's law that that would be proportional to the temperature gradient. Yeah, let's see. Okay, we got two different things here. I'm going to put 2. Okay, we know that it's proportional to the temperature gradient. And we know it's a negative, so minus k times the temperature gradient. And if it's radiative, that means that the hotter it is, the faster it bleeds heat. And so it's also equal to a constant times the temp. Okay, so those two things would be the same. Okay, let's think about it. I have to think about, I'm going to have to think about du dx is going to be some kind of a constant. I have to think about if it's positive or negative. Du dx at 0 t, it's got to be a constant, times u at 0 t. Let's suppose it's really hot. Then the fact that the heat is flowing out means that the du dx, well, that would be positive, right? At 0, which is the left-hand side, let me put a C here. Right, if it's hot, then the heat would be flowing out, and so the slope would be, the gradient would be a positive slope because it's flowing out to the left. So that C would be bigger than 0. But at the other end, du dx, say at the other end, pi t, that would be a negative constant times u of pi t. Because if it was hot over there, then it would be flowing out to the right, and the du dx would be negative. So this is the left end. Anyway, you got to think like an engineer when you do this and come up with the proper boundary conditions. This would be the right end. And those correspond to a radiation kind of event on the endpoints. Anyway, those Sturm-Liouville problems are really interesting, and you get some totally wild generalized Fourier series out of those. Question?
On the left end, what does the slope mean? Like, if we want heat to flow out to the left,
right,
we want the slope to be negative.
That's right.
So then on the left, shouldn't C...
No, to the left. Let's see. If it's hot, then it would be hotter to, let's see. If it's hot in the middle, let's say it's hot in the middle, and then it would be colder out to the right and left. And so here's 0 and pi. The temperature is flowing this way. So if it's radiating, then the temperature, then the heat would be flowing out, and so the temperature would be hotter. Yeah, the temperature gradient would look like that, right? Du dt is positive, and this way the du dt would be negative, and so it looks like that to give me the flow properly. So this would be the u. Okay, that's enough of that. I told you today I wanted to think about the vibrating circular drumhead problem. Vibrating circular membrane. And this is an example in science where the Bessel's equation comes up. Whenever you have radial symmetry in the Laplace equation or the wave equation, or etc., Bessel functions pop up. And it's interesting. They turn out to be the fundamental frequencies. The fundamental frequencies turn out to be the zeros of the Bessel function, which are pretty interesting. So let's see. I'm going to make this drum. I'm going to make it a unit circle drum. And so I'll have the origin. I'm going to make it be radius 1. And so my circular membrane, I'm going to stretch between a drum head that's a circle. So there it is. And so the wave equation for a vibrating membrane is, you guessed it, du dt squared equal speed of propagation squared times the Laplacian of u. And you know, if you screw down a drum head to the rim, you're holding the membrane constant on the boundary. Okay, so the boundary condition is u restricted to the boundary on the circle, on the rim. And then we'd have an initial shape. If I hit it with a drumstick, that would make a dent in it, so there'd be initial displacement, and whacking it with the stick would also give it initial velocity. So we'd have, let's do this in polar coordinates. do it in polar coordinates. Then I would have u of r1. No. So I've got polar coordinates. I'll have u of r theta. And so this is the boundary condition. And so the boundary condition is u of 1 comma theta is always held at 0. And then we have initial conditions. Which I'll call IC. The initial conditions are u of r theta at time 0. Let's see, I should have had a t here. U r theta t, and this boundary condition would be 1 theta t is identically equal to 0 for all theta and t. And the initial conditions would be u of r theta t is a something given. I'm sorry, r theta 0 times 0 is a given function, f of r theta. And of course, they have to be 2 pi periodic in the theta to hook up. Otherwise, you'd rip your drum. And the initial velocity would be du dt of r theta. T would be 0. That would be another given function. No t. That's the basic problem. And in polar coordinates, the Laplacian, let's take the c to be 1. So I don't have to write c squared all the time. In polar coordinates, the Laplacian is gives, let's see, we're going to have d2u dt squared, but in polar coordinates, the Laplacian is d2u dr squared plus 1 over r du dr plus 1 over r squared d2u d theta squared. Okay, so that's our PDE. So, of course, by analogy with the string problem, the Bernoulli method is we'd try, the Johann Bernoulli method, try u of r theta t equals function of r, call it capital R of little r, times a function of theta, which I'll call capital theta of little theta, times a function of t, which I'll call capital T of t. Okay, now I plug it into the PDE. And I would get r theta t double prime when I take this second derivative with respect to t. And I want that equal to r double prime theta times t. The r derivatives would pile onto the r function. Then I'd get 1 over r prime theta t. And the last one would be 1 over r squared. This time, the theta derivatives would pile on to the theta function.
Should it be t double prime instead of t squared?
Definitely. Thank you. There it is. And you stare at that for a minute and try to figure out how the heck would I separate variables there. Eventually, you'd probably try multiplying by r theta by 1 over r theta t. So I'm dividing by r theta t. Divide the equation by r theta t. Then I would get t double prime over t equals, let's see, what do I get? R double prime over r plus 1 over r, r prime over r, plus 1 over r squared theta double prime over theta. And you stare at that and realize, oh, I've seen something like this before. This is a function of t. And this side is a function of r and theta. Well, now if I think about, okay, why don't I hold, let's take t to be a half. Then that left-hand side would be a constant. And so the right-hand side would always have to be that constant if I stick in t equal half. So sure enough, we come to the conclusion that this is got to be a constant, lambda. And now that I know that the right-hand side is constant, now I let t move again. So I deduce that constant lambda, we get lambda by holding t equals a half, or some fixed number. Now that I know the right-hand side is constant, the left-hand constant has to be constant too. So the right-hand side equals lambda constant. And now let t move again. So we let t go free. We see that the left-hand side is the same constant. So that's the reasoning. Okay, so that left-hand side is an easy equation. So we get the t problem, which is t double prime minus lambda t equals 0, and no other conditions. That's easy. So we'll save it for last. We can do it any old time we want. Now let's think of the right-hand side. The right-hand side is 1 over r squared, r double prime over r, plus 1 over r, r prime over r, plus 1 over r squared, theta double prime over theta.
Is there 1 over r squared in front of the r prime, r double prime?
Isn't there? Nope. Did I mess something up?
I don't think there's 1 over r.
You're right, there isn't. That's not the... And those are equal to lambda. Okay, so interesting. I've got a function of r floating around, and the other thing there is a function of theta. So and now I'm going to multiply by r squared. that what I'm going to do? I'm not going to do that yet. Wait a minute. Yeah, I'm going to do that. I get r squared times r double prime over r plus r times r prime over r equals theta double minus theta double prime over theta plus lambda r squared. So I put, no. Plus, I got to put the lambda r squared on this side. So I multiply by r squared, and I'm going to put, thank heavens I'm almost out of time, minus lambda r squared equals this. So I multiplied by r squared, and I pulled all the r stuff to the left and put all the theta stuff to the right. And so now I realize, aha, once again, I have a function of r equal a function of theta. They both have to be equal to a constant something, mu. And so now I've got two ODEs, and they're rather a famous ODE. So the theta ODE, the theta problem is going to be an easy one. We've seen it before. Let's see, it's going to be theta double prime plus mu theta equals 0. And of course, we don't want the drum to rip. So the theta problem is, if we're going to get no kinks or rips in the drum head, then we better have periodic boundary conditions. For the theta thing. Okay, so that's going to be an easy one to do. We've done it before. It's easy. We've done it before. And so now we're back to the R problem, which is going to be interesting. So what did I get here? The R problem is r squared r double prime plus r prime minus stuff. Minus mu plus lambda r squared times r equals 0. That's a famous ODE called a Bessel equation. And that's where they come up in history. And it's a famous differential equation that's been studied to death. It's just as good as an Euler equation. The solutions are just as explicit. They're power series. They converge just as fast as sines and cosines.